Okay, I think we'll have to start. I'm not sure if Ian and the others from the group will be attending, but I think we'll just have to start for now. Okay. So we're going to have a meeting for the flight control team, and to start, I think I'll basically describe the things that we'll be doing for the flight control team. So recently we flew our N1 rocket, and it had no active control. It just relied on aerodynamic stability to keep it oriented straight so that you could get the maximum altitude. So for the N2, we are going to implement active control, and there's a number of ways we can do it. We can include movable fins. We can do gimbal thrust through thrust vector control, or adding a thrust fin to control the direction of the exhaust gases, or a vernier system such as coal gas and such. So for movable fins, we can either move the tail fins, we can add some wings which you can control, or we can use canards. So for canards, we can move the entire wing, or we can include a rudder system. The reason some people include the rudder is because moving the entire wing can sometimes cause vortices which will interfere with the tail fin. When the entire wing is moving, when the entire canard is moving. So the canard are the wings that are at the front of the rocket, the top side. This is an example of ruddered tail fins. Yeah. This is an example of how to implement cold gas thrusters. So yeah, I think I'm just sharing the systems that we have as options to control the rocket. And this is a reactional system, which controls the rocket by conserving angular momentum. So the mass is being rotated using motors, and that affects the orientation of the rocket, the attitude of the rocket. Okay, so such a system is relatively easy to implement. The only difficult parts might be the machining of a weight which can control the um, the the attitude of the rocket. Also, due to space constraints, we cannot include such a huge system for the N2 because the N2 is a small one. But we could possibly include just one of them to control the roll. Yeah. Another thing about such a system is yeah, they're affected by saturation, meaning that when the way they work is to conserve angular momentum. So when a force is applied, it counters it by rotating by varying the speed at which the mass is rotating. So saturation comes whereby the motor is already rotating at maximum speed, and that still doesn't restore the origin, does not counter the force to restore it to the desired position. These systems are common in satellites. Okay, this is an example for thrust vector control. Okay, so for thrust vector control, uh, uh, the engine is gimbaled, meaning that it can move about a given axis. It has a degree of freedom which is assigned by the gimbal, which is holding the engine. Usually 2 or 3 axes. Okay, so by controlling the direction which the motor is pointing, you can affect the attitude of the rocket, meaning that you can control the direction in which the rocket is going. Okay, so for those are the examples for the systems that we'll be implementing that we could possibly implement in the N2. Now for thrust vector control, the problem with it for the N2 is the size of the engine as it is currently designed. The engine as it is right now is too big for thrust vector control. To include a gimbal on it will increase the size of the rocket by a big degree, which might affect the target for the N2. So right now, what we're going to do as a team is we're going to be working on the system that will fly on the N2. And for a start, we'll be including sort of control for the N1. And this we hope to be doing by Canada. There's a bit of work that we had started during the internship. You can find the repository on the Nakuja Project GitHub under N2 active fin control. So we wanted to implement canards to control the attitude of the rocket. Yeah, to do this, we were to use IMU, that's an inertial measurement unit, which contains a gyroscope and an accelerometer. Such a system in a chip such as the MPU 6050. And by reading the sensor values, we were to affect how we are flying the N1 and to improve the stability and as well as reduce the roll and the pitch of the rocket, such that we can extract the most out of the rocket. So for the N2, I think currently we're in the prototyping phase. So we're going to be using GitHub generally for coordination. We'll be for prototyping and testing our systems. I think you can use MATLAB or Python. And yeah, testing the prototypes on Arduino. And yeah, we had also been looking at using this controller, the EDB5. It contains an MPU 6000, MPU 6000, which is also an AMU. The way it differs from the MPU 6050 is they're generally the same. The only difference is that MPU 6000 has both I2C communication as well as SPI, meaning that you can utilize the full sampling rate of the gyroscope, which is 8 kilohertz. So I think, yeah, that is the target, but for prototyping, we'll be working with Arduino. Okay, I think that is all for now. I think I'll hand over to Dr. Oki because he had a presentation for the group.
Oh, okay. Thank you very much, Sami. It was a very fantastic presentation. Mine is will be very short. So let me share my screen. Oh, here. Oh, oops. Just a moment. Yep. So can you see my screen?
Not yet.
Not yet?
Yeah.
Okay. Maybe because of the permission. Okay, maybe you can just proceed. Yeah, I will try to sort it out.
I think I have the presentation. Maybe I can share it for you.
Yes, please. Let me, do you Yeah, this one. Can you open it?
Okay. Yeah, just a minute.
Okay, thank you very much. So, as Sami has explained, what I have not covered here is okay. There are in some slides there were four, like fin control, TVC, and cold gas jet or side thruster, as well as vane. But the last one is not covered here because it is not commonly used. And what I have researched last week was aerodynamic control, which is fin control. Especially we are working on the low altitude rocket for now, for M2. So next. So as Sami explained, the rocket may have three positions in terms of the wings. So the front is called as canards, as Sami indicated, and it is rare, but some, okay, actually I have researched about missiles, not the rocket. So missiles are supposed to have wings sometimes. And also the tail fins is a common way to control the posture or attitude of the missile. And there is a pro and con. So for example, the canard control. So if we control the front wing, so the response will be very fast, but there will be a risk of oscillation. So sometimes it's unstable. So it takes time to converge the movement or the vibration, like pitch movement. And instead, we can utilize the tail fins as well, so that even though the response will be a bit slower, so there is a delay between the command and actual movement. However, it's very robust to oscillation. So I decided to make a simulation for the tail fins, but it's just a matter of the equation of the motion. So I think I can easily apply my simulation to canards. Next. So before going to the content, let me talk about the difference between guidance, navigation, and control. So there are, even though there are not specific definition, but the book I was reading mentioned the difference. So maybe start from the navigation. So navigation is basically getting the attitude and the position. For example, X, Y, Z, the position, and also the angular rate, like a roll, pitch, and yaw, using the IMU. So this is called as navigation. So what's a guidance? So guidance is, okay, this is a book about the missile design. So they are talking about, so can you see the homing seeker? So what is a homing seeker? It is going to track the target, like airplane or ship, to track the position of the target. And then the guidance system or guidance law decides which position the missile should go to next. So this is a guidance. And then, so basically the guidance decides target position, then it will send to the control system. So the control system, so by receiving the target position, it's going to control the position and attitude of the missile. So this is a difference. Next. And again, so yeah, so I was thinking, I was researching about basically about the initial guidance or initial control. So what is the initial control? So this initial control is triggered 1 or 2 seconds after the launch, because the rocket has, so basically what is the problem of the rocket? So basically once the rocket is launched, so it's going to rotate. So this is a roll movement, and which is going to cause a failure at some time. So we try to suppress this rolling movement. And this rolling movement, if it happens, it's it is a bit difficult to control the pitch and yaw, because we cannot distinguish the pitch and yaw. So it's better to suppress the roll movement. And also the pitching angle is concerned with the flight path angle. So it's related to the destination of the rocket. So we have to adjust the pitching angle as well. Next. So could you play? So this rocket utilizes a control system which suppresses the rolling movement. So immediately after the launch, so the left one is unstabilized, the right one is stabilized. So you can see the right one is not rotating. So because of the fin, so just after the launch, the fin quickly, moves to suppress the rolling movement. And I did a simulation for this. Next. Oh, and but again, so why the rolling movement is a problem? So actually, there is a phenomena called as roll locking or the roll pitch resonance. So once this happens, it's going to oscillate. The rocket is going to be out of control. So we try to control the rolling movement. Next. So there are basically two basic methods, like classical control, PID, and a modern control, which is optimal control. However, if it doesn't work well, we can still utilize a reverse control, adaptive control, or model predictive control, which is more advanced. Next. And so how we can control the pitch and yaw and roll. So this is related to this airplane. So I hope you know how the airplane is controlled. So it's going to, it's using an aileron, rudder, and elevator. So this is, even though the rocket tail fins has only 4, it can distinguish. I mean, it can, as shown here, you can control the pitch and yaw and roll. Next. So this is the equation of motion. So I didn't indicate what is alpha, q, beta, but this is basically when you read a textbook of the flight mechanics. So it's a common. So alpha is the attack of angle, angle of attack, sorry, and the q is pitching rate. It's the angular velocity. Beta is a side slip angle. R is so it's a PQR, so it's a yawing angular velocity, yawing rate. The P is it's a PQR, so P is a rolling movement. It's a movement around the x-axis. So the typical parameter aerodynamic coefficient is shown in some books or the paper article, so you can find such a value. Next. So this is a control system I have referred. So this is a typical control system for the for suppressing the rolling angle. So the left, top left, there is an equation for rolling motion. So by using a Laplace transform, we can calculate the transfer function. So this is I named it as G2. So G2 is the transfer function of the rocket itself. So it's the input is elevator angle, and output is pitching, rolling rate, rolling angular speed. So, and also there is another transfer function which is G1. G1 is a transfer function for the fin device. So the input is a target angle, and output is output angle. Yeah, so there are 3 internal loops you can find. So in the G1, there is a damper loop to suppress the oscillation of the fin device. And there is an outside loop from G1 output, which is for the angular rate velocity. And the last one, the last external loop is angular angle control loop. So there are three internal cascading loop. Next. So so this is a transfer function of the actuator, which is a fin device. So I took the value from some literature. Next. So finally, I did the simulation using the control system, which is shown 2 pages before. So the red one is angular rate p. Yes. So what this is a step input response. So I inputted the target angle is 1 radian. So at the end of the day, the phi should be 1. And you can see the blue line is going to be stable, exactly 1. And so p is the rate. So this is the speed. So it should be 0 at the end of the day. And you can find the red response is going to be converged to 0. So it worked. So this is a simple simulation I did. And I hope, even though this is a very, very simple P controller with some feedback, but yeah, we can start from this kind of very, very simple control system, I guess. That's all. Thank you.
Okay. Thank you, Dr. Oki. Yeah. So I think so. What the last thing we need to do is to find the appropriate meeting time, which we'll be using regularly. So I propose this current time on Friday from 1 to 2, if that's okay. Some convincing.
Yes, yes.
Okay. Okay, so if everyone is okay with that, so we'll meet again next week. We'll be on the next meeting. We'll have assigned the tasks to be done. So the tasks to be done are generally first for testing on the N1, and then the task to be implemented for the N2. So generally, we'll be focusing on Canad and fin control. So I should look for material relating to that and research so that when we start the work, everyone will be okay with that. Also, I think I had mentioned simulations on MATLAB, Python, and programming for the onboard system, C, C++, Arduino. So I think just get familiar with these things, as well as software such as OpenRockets and yeah, other things like CFD. You can use ANSYS or CFD Ultimate by Autodesk. Yeah, I think that's it for today's meeting, unless there's someone with an additional comment.
Sorry, I was not hearing the middle part, but so maybe what was agreed tasks by next week?
Yeah. From now, just it's just to get familiar with the systems, and then we'll be assigning the general tasks on next week.
Great.
Yeah. Okay. So look out the GitHub, and other forums will be communicating on WhatsApp as well. So that's it. Thank you, everyone.
Thank you very much.